All right. Welcome back, everybody. This is Hired Labs Coding Bootcamp. We are in week 2. We are talking about algorithms and data structures. We're in day 4 overall, where we're going to be evaluating those algorithms and data structures. We haven't really talked about data structures so much. We will today. We talked about algorithms a little bit, and I left you last time with a problem set with some algorithmic problems to solve. And so you had to write your own algorithms to solve the problems that were in there. And they're all uh, picked to be things using mostly lists and strings and that sort of manipulation, and should be good low level or beginning things to start off with. Anybody get a chance to do any of the problems from that? No?
Yeah, I did.
Did you?
Yeah.
Cool. How many did you get through? Do you knock out all 20, or you get through?
I did everything except like couple, which I
Okay.
didn't understand.
Okay. Okay. Cool. Do you have any questions about them? Did you get hung up somewhere that you want to talk about?
Um, so uh, there was some question that I didn't understand. Um,
What it was asking you to do?
yeah,
Okay.
pretty much I didn't understand the prompt. That's why I didn't do it.
Okay. Okay. Cool. Did you run into any general problems along the way though, like while you were solving them, or did you find those pretty simple?
Yeah, pretty straightforward. It was
Excellent.
fun.
Excellent. Excellent. So yeah, if you blasted through those, I would definitely recommend looking at some higher level ones. Those both those sites that we send out have like literally hours and hours and hours of those things to do. And the ones that we send are again the very, very beginning. So if that's easy for you, um, keep going until they get hard. And also there are similar structured things on freecodecamp.org that we put in the free coding resources down at the bottom, very similar structured, like solve an algorithmic problem thing. So for those of you that haven't, make sure you're doing it. Make sure that you're practicing those problems. It is the best way to get a handle on these, get used to the syntax, get used to the way strings and lists and all those things operate. Again, even if you're not going to be doing this full time as a developer and that's not your goal, it's one of the best ways to get your hands on with the syntax and really understand how it works. So practice those problems, do those things. And then with that, we can go quickly over a review of what we did up to now. So sort of like when you're watching a show and they say previously on whatever, we're not going to go over absolutely everything that we've done up to now. We're going to kind of highlight the things that are going to be relevant to our discussion today. And so one thing that we definitely brought up pretty much every time is the way we've talked about data in several senses. And today we're going to talk about it in a third sense. But so far, the first time that we talked about data, who recalls what we talked about the first time that we talked about it? When we defined data from like the week one, day one. What's that?
Binary.
Binary. Yes. Yes. Very good. So computer storage binary. It's how things are stored in memory and in storage, which again, if you recall, memory is something's persistent, or sorry, memory is not persistent, excuse me, and storage is persistent, but they're both similar functions. They're storing something and keeping it for a time. And then it's also relevant in our CPU usage. We talked about that, the calculation, how that's done, how much time that takes. We're going to talk about those things today a little more, about the implications of those things specifically on memory and CPU usage when we talk about data. But then the other way we talked about data, when we talked about data types, who remembers what sorts of things we talked about when we talked about data types? What does that mean generally? Like even with an example of a data type.
Like integer? Is it
Yeah.
type?
Yep. Yep. Exactly. So when we talked about the basic syntax of Python, we talked about things like integers, floating point, the decimal point numbers, right? Booleans, all those sorts of things, lists, dictionaries, classes is where we ended up. Those are all data types. Functions are also data types. So that's how we talked about data as well, right? As is the way that Python understands and the way that we communicate through Python with the computer, and we communicate real ideas like numbers and words and things that we use in real life. That's another sense of data, the data types. Um, and let's actually exit out of this real quick. There's really not a whole lot of slides. That's kind of the last slide until we get into our next concept. But also in by way of review, I'm going to slide over into our main.py file and talk about the class and the structures that we did up to now, right? So go back into Python anywhere, going into files up here from the dashboard. We should at this point have our main.py and classes.py. And if you recall, I'm just going to open both of these. So remember our classes.py has just our class definitions where we ended up, where it was just our car class defined. And we refactored our code to take in these arguments as a list. You remember we talked about this as the data type that this is. It's a list. So it's what are the things that we remember about lists that are very important?
They're in order.
They're in order. That's one thing. What's another thing that we talked about? Maybe don't remember, but we talked about them being. Can we change them, or are they mutable or immutable, as we call them?
Mutable.
Yes, they can be changed, right? So those are the two things that we really got to remember about lists, that they can be changed and they are ordered. And then we also refactored with keyword arguments, which, if you recall, the data type was what? What data type is this? As opposed to lists. Lists were the arguments. This is the keyword arguments is what kind of data type?
Is it wait, string? No.
Nope, not a string. String is something that's just separated by, or
It's not a
it's
dictionary, is it?
Dictionary?
dictionary. That's it. Yes, dictionary. And remember, dictionaries are defined as what? What's the main thing that we got to remember about dictionaries?
Key and values.
Key value pairs. Exactly. Key value pairs. So we left it with calling the keyword arguments dictionary by the key. Excuse me, to get the values that we needed. And our self-referential string that tells us where we were, right? And then we routed all of that through. Excuse me, sorry, I have too many things in this. We routed that through our main.py down here with our input statement and the import up here at the top, right? So that was where we ended up last time. Now today, wait, before we move on, do we have any questions about that, about the class itself, about any of the things that we've covered up to now? The condition, the control structures that we covered, the if, elif, and else statements, the loops, the for loop, the while loop. Any general questions about that before we dig any further?
Is there any type of spell check on here, or is that up to us?
That's generally up to you. I think. I don't know. I'm hoping this might actually be spelled wrong. But I think the most kind of check stuff that they'll do is if you save something, it'll throw up these little flags that'll say, okay, this isn't defined, whatever this is. I put an at or a semicolon, so that's separated things. But text editors generally will do that sort of thing where it's not really spell check in the sense of English words or something like that, but it'll check for the proper syntax of Python. And so if you have what looks to be a variable name like this, to the interpreter, it's like, well, this probably is a variable name. It's just not defined anywhere. So like that's about as close as you're going to get to a spell check, I think. And then these reserved word things that'll help you out.
Cool.
Cool. Good question. Any other questions about what we've done up to now? All right, great. All right, so last thing, I could go back to slides, but just a single word, recursion, is where we're going to go today. So where we're going to start. So we're going to talk today about some optional ways to do things and talk about the choices that are being made and how we make these choices when we're designing our systems and we're doing things. We're going to have a little discussion about design as well. So we're going to take this idea, we're going to start this idea of recursion. First of all, does anybody know what this is? Anybody familiar with recursion already and could define it for us in some way? So Aurelius confidently saying no. I can't see anybody else. Anybody else got an idea of what recursion is? Ever heard of this term before? No? All right. So something happens in several contexts, and we see it all over the place, actually. We use it every day. I'll talk about that in a minute, but it might be helpful to show you what it is first as an example, a visual example of recursion. So to do that, I'm going to go over to this Google Meet page, which you should all see, hopefully this Google Meet thing says new meeting. And when I start this meeting, what's going to happen is it's going to hopefully give me a warning that says, and hopefully they haven't solved this problem. The reason I'm not doing this on Zoom is because Zoom's fixed this. But when I start this meeting, it's going to give me a little warning when I try to share my screen that says, hey, you're going to start what they call an infinity mirror. Say this little warning says infinity mirror. To avoid an infinity mirror, don't share your entire screen or browser window. Share just a tab, blah, blah, blah. I'm trying to make an infinity mirror. This is recursion. So I want to show you what this is. I'm going to dismiss this warning. Hopefully it doesn't crash my browser that I'm running in because it's going to take a lot of my power to do this, but we'll see how it goes, right? So when I hit dismiss, this is my screen over and over again. You see it's the entirety of my screen repeated within itself infinitely down to this tiny, like you can't even see how small it gets. That is recursion. It's visual recursion. So the image of my screen is recursively within itself over and over again. So this idea of recursion is something that's really cool. And we use it all the time. I'm going to stop sharing on that. I'm going to close this out. Otherwise, I'll end up actually breaking my stuff probably. And the reason, so recursion as a concept is an important one. Yeah, exactly. We entered the matrix. I see your comment there, Corey. It's an important one in the sense of it's something that we do naturally, but it's kind of a slippery concept when we think about it applied to like computer science. But again, we got to try not to overthink it too much, right? So we're using it in language right now, or I guess I am since I'm the one talking. But when we speak English, it's one of the things that makes human language separate from animal language is our ability to recursively add like a sentence within a sentence. You know, you can always make a sentence longer by doing what I just did. When I just said, you can add, you know, or I heard that, or she said that, or something like that. And sentences don't have a length that makes them no longer a sentence that's like bound by something, right? And that's recursion that allows us to do that. In computers, recursion is generally something where it's like referring back to itself, right? So we're going to go through an example of refactoring this while loop into a recursive function. And the reason we're going to do that is I'm going to show that there's multiple ways to do this, right? So you could do a while loop, you could do recursion. You don't really have to do recursion if it's not something you want to do, but it's going to lead us into the discussion of why we make a choice, what choice we're making, and how behavior might be different, even though you're trying to accomplish one task and there's multiple ways to do it, right? And we're starting with recursion because it's a really common thing when we start talking about algorithms and named algorithms that people use. Recursion and recursive functions is a really important thing to understand because that's a way a lot of them work. They are grouped as recursive functions. So before we dive into the example of this in code and how we would do recursion in Python and what it looks like, any questions about the concept of recursion and what it is generally?
So like, what does that mean? What does recursion mean in like layman's terms? Like if you, yeah.
It's something that refers back to itself or contains like a version of itself. Does that help or does that make it more confusing? Okay, cool. Anything else? Any other questions?
And you're gonna show us how like how that we're going to incorporate that with like or whirl or loops and stuff like that, or no,
Yeah. So we can implement it by doing, we can rewrite this. So what we're going to do is we're going to refactor this container filler function that we've got here. Again, first of all, to clarify, you guys can see my screen back on Python anywhere, right? I want to make sure I'm doing that before I start talking about here and there and stuff on my screen. Yeah. Okay. Cool. So yeah, we're gonna refactor this container filler function to be a recursive function and not use this while loop, right? So we're gonna rewrite it doing recursion the way it is, and we'll see that it's just the function referring back to itself. So let's go ahead and do that, and this will hopefully make it a little bit clearer on what it is happening here, right? So make this maybe even just a little bit smaller. All right. So we're going to define a new function. And this time, just to remember that it's a recursive one, we'll call it a recursive filler. And it's going to take a maximum again. We're going to pass some maximum limit, except this time we're also going to pass it the count, right? So remember this last time when we used the while loop, we set the count when the function started. We could have optionally passed this as well up here, but you know, it works just as well doing it here because, excuse me, the loop part was done separately and we made a count here. Should equal, yes. Question.
I feel like you already said this, but I need to make sure I'm clear in
Sure.
Coding is not good for me because I need to know why everything is.
That's totally fine.
So-
That's what we're here for. What's up?
So the recursion, why, I mean, other than like what you showed in that demonstration with the Google Meet,
Mhm.
why would you use recursion? Like, is it always like that infinity pool of stuff, or why would you use it? Or you're getting to
No,
why? you
yeah,
use
I'm going to kind of get to that. That's the thing is that, so I'm
Okay.
going to show you sort of how we'd implement it, and it'll hopefully make it a little concrete about what it is in this context. And then the whole point of today is exactly that question. So it's a good question. It's a great question to ask. Is like, why would we do one versus another? What choice are we making? And how do we decide which one is the right choice to make? So that's really is the point of this today. Is because like as you're learning to code, there are literally just hundreds of ways to approach everything you do, right? Even from the simplest decision of which coding language you're going to start working with, right? If it's like we chose Python, and I told you the reasons that we started with Python, and if you're still confused as to why, we could talk about that more. But every time you go to work on something, that's a decision. If you're going to use Python or you're going to use some other language that's similar, like JavaScript, to do what you're trying to do, right? And every time you make a choice, it should be for a reason, and you should understand why you're making that choice. So today is exactly about that. We're going to talk about some things that are optional, like this recursive thing. You don't ever really need to do something recursively, especially when you start. It's a little bit somewhat advanced of an idea, but it's used to illustrate the fact that you can approach it one thing two different ways, and like what is happening when you make the choice. Does that help answer your question?
Yes, thank you.
Sure. But that's really, again, you're like 2 steps ahead, which is perfect. I love it. So, all right. So in this recursive filler, we're going to do the same thing that we did with our other filling box. We're basically just going to rewrite it again. Refactoring as a term is rewriting our program or algorithm application. So the function is basically the same as it was. And we're just going to have it written slightly differently. All right. So in this recursive filler, we're going to send a maximum, and we're going to send it a count. And we'll talk about why we send it a count here in a second. Just for now, let's just put in the count. We're going to send it as one of the things that we do. So when we write a recursive function, the first part that we want to start with is what's called like the base case or the ending case, where you want things to stop, right? So we're going to do this with a conditional logic control structure. So with the if statement, and we're just going to check some kind of condition to see if it's true. And if it is, we're going to tell it to do something and stop there, right? So if we think about our container filler, the stop case was what? Right here, right? Where we print out, that the box is full. So let's start with that on our recursive thing since we're refactoring, right? So we say if, and before I write this, anybody want to be brave and give me the logic that we want to use here? We want to check. What are we going to check?
If same,
What's same? It's close.
if the container has count out of, if that's the same, I'm kind of spitballing here.
Yeah. So if the count, right, is the same as what?
That's the same as the container.
The maximum,
If
right?
if the count is, the same as the maximum in
Right.
the container, yeah.
Yep, there you go. So so this is the logical statement that we want to make. And remember, we want to use the double marks here because this is like saying is equal to, not if we use just one, that'll be a mistake because it's setting something. Then we get the colon, it's going to do 2 indents in. Remember, indentation is important in Python. So we're 8 spaces from the end or 2 tabs or spaces, don't mix them. All right, now we're in the if statement. So what we want to do is once the count is solid, we're going to do this. We're going to print out the box is full. So I'm just going to copy this from above since we are refactoring. I'm just going to copy and paste it into that indented block. So first line, we're just going to check to see if the count equals the maximum. Then we'll say, all right, box is full. And it should stop right there. Right? And then in our else statement, we are going to do the rest of the parts that we had basically in our while loop, right? So we're going to adjust the count, do the same overall process. We need to adjust the count in some way, give ourselves some sort of, information about where the count is at this given moment, at this particular step of it that we've gone up by 1, and then give ourselves confirmation that we have. And then we want it to loop back and do this again until it reaches our ending point. So we need to do all that logic here at the end of this. So let's start by changing the count. We're going to do that in the same way, right? So we do count, increment up by 1. And then we're going to give ourselves this, and again, I'm just going to copy this because it's the same print statement, just giving ourselves confirmation out to the console. If you remember this isn't a return statement. It's not the same. It's just printing out for us to understand what's going on. And then the recursive part. Now, this is where the quote unquote magic happens. And it's going to be somewhat anticlimactic because it doesn't look all that cool. But what we're going to do now is we're just going to call this function within itself. So that's what we're going to do. So we're going to evoke the function the way we've called our functions in the past. We're just going to do the name, recursive filler, open and close parentheses. And then we're going to pass it the parameters that it expects to have. It expects to have our parameters. And if you remember at this point, we haven't changed maximum. We haven't done anything with it. We've just checked it against our count. And then at this point, since we know that they're not the same in our algorithm, once we get to this condition, we've increased the count by 1, right? So now the count is higher by 1. So we're going to just pass our maximum, and we still call it by the same name because it's going to be the same number it was here, same number it was here. It'll remain that same number. And then we're going to pass it our count because it's the same number that was passed, except up by 1. And if we didn't do this little section right here, we could have just done count plus 1 directly in this, but this will give us our each step confirmation by breaking it out this way. So this right here on line 36 is really where the recursion happens, is calling the same function that we are in. So it's get down to this point, and it's going to call itself again. And basically what happens here in the computer side of it is that the first time this comes through, it's going to read all the way through. And if this condition is not met, it's going to move on to this condition, and it'll do each step of this along the way. And when it gets here, it'll run this function, and it'll wait until it runs again. And it'll go all the way down until this condition is met, or you run out of computing power, and it stops. So that's how this recursive function is going to work. And it like winds all the way back and executes all these that are waiting for the next one to run all the way back up to the top. So any questions about this before we test it and see if it works the way we expect it to? All right.
No.
No. Cool. Okay. So I just commented out, as it's called, all these sections, all these lines between 40 and 43 by just highlighting all of them, then hitting Control and slash. And that's a way to toggle comment or not comment. That way I don't have to erase all the code. I can just not run it. So that's what this is going to do, is going to ignore it. So that's a pretty handy little hotkey for all these text editors that we use. And that's common every text editor. That's not just Python anywhere. All right. So now we're going to do our recursive filler and give it a test. So let's say recursive filler, and we'll give it a max of 5, and the count will start at 0. So it's an empty box, should fill up to 5. We're going to save this, and if I run it right here in the browser, I mean, I can just go back to our console and run it from there. Or a bash console, if you recall consoles, then in bash. And we are going to run our Python 3 main.py command. And as you can see, it functioned the same way that it did in the past. It ran through and gave us each item at a time in the container, and then said the box was full once it matched the 5 items. So this is an example of refactoring what we were using before as a while loop as a recursive function. So any questions about how we did that mechanically and syntactically? Any questions about this construction and how this works and what's going on?
Well, I guess I'll have one for after. I tried to run it or save it, and it gave me an error.
Uh-oh. What error did it give you?
It says trace back file. It says a lot of stuff. And it says file.
Okay. Okay. All right. Yeah, if you don't have any like warning flags in here, like any red X's on the left-hand side or yellow triangles with exclamation points, then it could be something you need to look in that bash console for. But check that first. Check in your file, because this text editor will give you those little warning things. Yeah, really. So what do you got?
I made my count 5 to 1, but in the bash it's showing 2 to 5. Is that because I didn't put a 0? Like 5
Oh,
and
so you
0?
started with one?
Well, I started with 5 and then went with the recursive filler.
Yeah.
5 and 1. Should I make 0? Because when I pull up in the bash, it says container has 2 items, 3 items, 4 items, 5 items.
Yeah. So check it out. Why would it do that? Why do you think that happened?
Because it needs to count one more back to 0 to kind of get the full count in.
Well, so you passed it, your input here looks like this, right? With the
Mhm.
recursive filler in 5.1. Okay, cool. So anybody without, I'm not gonna go run it right now, but here's the whole definition of the function. If you're not, if you're not playing at home and you didn't write your own, just looking at this and looking at my screen now, and Aurelius, you too. Anybody shouted out though, why would it start at 2 if you gave it an input of 1?
Because else the count plus equals 1. So it's
Yep.
already counting as 1.
Yep. It started at 1.
Okay.
So the first time it prints out, when it gets to this line, the first time it's going to be a 2.
What does the plus equals stand for again?
Increment.
Increments.
Yeah.
Okay.
So it's increment up, and then if we made it a minus equals, that's decrement to go down.
Okay.
But
Do you mind going up a little bit to where it says def container? Yeah.
yeah, sure. And again, yeah, this just so these two functions, the regular container filler that we did with the while loop and the recursive one, they do the same thing. They're doing this, they're accomplishing the same task. It's different approaches to it.
Okay. Yeah, because I got the little X and I was like, what did I do wrong? All right.
Yeah. Okay. Yeah. And really watch for the indentation levels. That's usually the thing when people start writing with Python. That's one of the biggest thing catches folks is they have their indents aren't quite lined up where they expect them to be, and that can be a source of headache. So I want to show you a couple examples of what kind of goes wrong with this. We put in these safety parameters to say, move or count or don't, I told you don't forget to do that or it'll break. So let's break this a couple of times and see how it breaks differently between these two options. So I'm going to do first is I'm going to take this container filler and I'm going to comment out our increment. And then I'm just going to run it. So I'm going to do container filler. And I'm just doing a lot of copy and pasting now to kind of save us some rewriting and some time on these things. And I'm going to send it a maximum of 5, like I have been doing. Except this time, there is no change in the count. So it's going to enter 0. It's going to be 0 every time it goes through. This condition is never going to get met. And the system's not going to be happy. So I'm going to run this directly in here by just hitting this save up here and then run. I'm going to hit the run button, big blue button. It's going to open a console. If you've already got several consoles open and you're like past your limit, it may stop you. This may not have wanted to either. Huh. All right. Well, never mind then. Let's go back to our bash console and run it there. Okay. I don't know why Python anywhere didn't want us to do that, but we'll run it here. That's fine. It's all about the same. All right.
Yeah.
So it just kept running forever. All right. Yeah. Aurelius, you have a question?
I was saying I did it and it just kind of showing what you're showing there.
Yeah, showing this right now, right? Yeah, I don't know why my console didn't open up. That was just for whatever reason. But this is where I wanted to get. So this is the error that happens. It says printing so much that it's interfering with other users, and it's been closed. So womp womp. So that means my console's probably dead. I might have to go actually open a new one. I'm not sure I can do anything with this now. Yeah, I can't. So let me go back to my consoles. And I have no console, so I'm going to start a new bash console. But so what happened there was it said that I was basically using up all the resources. And so other users like yourself don't have any because you're being a jerk. So stop doing that. And it broke everything for me, right? So that was when we took out the while loop stop condition, right? So this condition was never met. The while loop, it just kept running and it said that we were using up resources and Python Anywhere stopped us before we crashed their resources, right? So now I'm going to do a similar breaking of our recursive filler by setting the number to some gigantic number and have it go through recursively way too many times. See if I can get it to run directly here this time. If not, I'll go back over and do it in the other place. That's okay. So I don't know why my console's not popping up here. It's not. It's all right. Oh. Python 3. main.py using tab complete to finish. Whoa. What? Did I miss an argument? Oh, count. Right. I got to start where it counts. I'm sorry. I forgot a positional argument there. So that's what this warning was telling me, that I was supposed to have 2 arguments and I only gave it 1. So let's try that again. All
I was
right.
gonna
So
count the one. Yeah.
yeah. So it was supposed to give, I was supposed to give it the 2 inputs, right? The container maximum and the count that it started at. I forgot to give the starting count. So it gave me that warning, the not enough things. But as you see, it went through just about 1,000 times, and then it decided, all right, broken. But it didn't break it the same way, and it didn't give me the same error, right? Because it's something else is happening under the hood, right? So we got recursion error, maximum recursion depth exceeded while calling this Python object, right? So that means basically it went too far and it broke. So in both these cases, though, what is breaking? Like, what is the thing that's being exceeded? In this case, it was the maximum recursion depth, right? And if you think about our recursive function, we went down, we do depth. Think about going from the top to the bottom of this function. And when it gets here, remember I told you it basically stops until the next run goes. So think about it going deeper each time, right? And then the while loop, it did something else. It said we were using up resources from everybody else. And so it stopped us. So what are the things that are being maximized or used up or pushed to the limit in both of these cases? What is it that we're doing?
The data is being capped out, or the memory or CPU one.
Okay. Okay. Which one do you think?
The CPU.
CPU. Yep. And why do you think that is?
Because I guess the number there was like 5,000 or 50,000. It capped out at, I believe, at 1,000. So it told me that, oh, that's a bigger number than I thought. But yeah, it's the memory couldn't store all that, so it just kind of gave you error. It counted what it could until it got to this, till it couldn't count no more, and it gave you the error.
Right. Right. Okay. So good. And that's the thing, is I'm not gonna say, okay, it's definitely the CPU or it's the memory. Like you said, it's one of those things though. It's those things that are being maxed out. Probably the memory in this case. But one thing I want to show you in Python Anywhere is you have an amount of CPU usage. And I've been kind of messing around with mine today. It resets every day, I think. I can't remember how many hours, 12 hours maybe. But I've used about half of mine. And so you can test this to see and run these things and try getting to that breaking point and seeing what your CPU usage is beforehand, seeing what it is afterwards. You're not really going to get to see if it's the memory, but if your CPU usage doesn't go up a ton, then you know it's probably the memory that you're maxing out, right? This right here, again, is storage, which, how's that different from memory? What's memory versus storage?
Memory is the run, and storage is what you can keep on there. Like how fast it's run, or is it the opposite?
No, it's not, isn't it? Does anything to do with speed?
Oh, well,
You're right. You're right there. You're close. It's so storage is.
well, I tried.
Yeah, you did. Is it okay? Is it stuff that stays between sessions or stuff that's used up in one shot?
Stuff that stays between sessions.
Yes, stays. So memory is temporary stuff that goes away when you close it out. Remember, if we go into our Python interpreter in here, actually, let me get out of this and clean up my screen a little bit. Sorry. If we go into our Python interpreter, and you remember we set a variable of some sort, and then we leave, that variable doesn't exist anymore, right? So we come back because it was just stored in memory. So say A is not defined, that doesn't exist because we quit, we left, it was just in memory, we didn't store it somewhere, right? So the storage was in memory. So when you're playing around those things and you look at your dashboard, you're not gonna be able to get to see how much memory you used when you did something, but you get to see your CPU usage and see if you're burning that stuff up and have an idea. But yes, the main thing to keep in mind is that as it's boiling down to bits and bytes, it is maximizing, it's using those resources, right? Any questions about those things up to now? Is it all generally tracking on this up to now? Yes. All right. Great. So the idea behind a lot of this is that when we're designing systems and we're trying to come up with our algorithms to solve whatever problem we're trying to solve, whether it's the problem set that I gave you or in an application that you're building or whatever the case may be. What we're trying to do is I'm going to go over here to our free coding resources and look at one of the examples that's down towards the bottom that I encourage you all to look at and read. It's on the reading list side. Down here below, some Python stuff. There's like some really good books on Python if you're into reading. This book right here, The Timeless Way of Building, right? So this book is written by an architect back in the 70s, and it's about designing buildings and towns in a way that makes them alive, right? And allows them to flourish the way that they do naturally. And his whole point is it's something that humans do naturally. And this has become a cult classic in Silicon Valley for design and software and all this kind of stuff, right? So the way that this guy approaches design for buildings and towns is directly applicable to systems design and any software design and things like that. And it's used very frequently for that purpose, right? So this is something I really recommend you taking a look at. It's set up in a way to be treated kind of like a reference book, not a novel, right? You don't need to read every single chapter, every single page. There's something that you can read in an hour, the detailed table of contents. I think it starts on page 9. There's a free PDF in here that if you start on page 9, it's about like 6 pages, I think. It goes page 9 to page 15, where it's like the really important ideas that are boiled down. You can read those. If you read the entire book all the way through, it kind of elaborates on those points. But the idea is that you can just spend about an hour flipping through that part and then go back to as a reference as you're attacking your design problems, whatever things you're trying to design. But the key that I want to take out of there, and I really encourage you to check it out when you got the time, is this concept that he puts forward that anytime you're designing anything, you're trying to come up with a configuration that's within a certain context that allows conflicts that arise in that context to resolve themselves. And that's really your goal for anything you're doing. So when we talk about what we're doing when we're designing our systems and our software, which again, so next week we're going to start building our application, and we're going to kind of slide through the design phase and assume that we've done it because this isn't a design course and we don't really have time to do all those steps. But from a development standpoint, when you were trying to, again, solve algorithmic problems and build the thing you're trying to build, you're going to be making choices. And this concept of configurations that allow forces that arise in a context to resolve, really important, is keeping in mind the context. It's very important to what is the right choice, because this example of recursion or a while loop, there is no right answer. Like I said, you don't really need recursion. You could probably go with just while loops whenever you need something like this for quite a while and be totally happy, and it's good. But there may be scenarios, there may be contexts where recursion is the best thing to do. It may be the best answer. It may be the best way to go. So how do we decide? How do we know what's the best answer? We saw that both of them break at some point. So what do we think we might use to decide which one of these we want to use? Now that we've seen both of these, if we were just kind of spitballing, what do you think?
Yes, would it be determined by the type of application you're building?
Absolutely. Yeah. So there you go. So context, that's for sure. What are the things you think you might use?
Because they don't really look like when you do the while versus the recursion, like it's not like either one of them are less steps.
Right.
So
Okay. Yeah. So like visually, it's about the same amount of code written, right?
yeah. So
And like we said, we could have, if we took this step out and not gave ourselves the information, we could just do like count +1 and save ourselves a couple of lines of code. But that's again sacrificing the update. But yeah, okay. So there's no real benefit there. Okay, cool. So any other ideas on what we might use to size up like what choice we make in here? So we know there's options and we got to choose. We're not going to do both. So like, what do we choose? What do we choose?
What we choose between the containers and like what's being written.
Yeah. Okay. Wait. Explain more on that. What do you mean?
No, I was asking. I was asking
You're asking? Yeah, I'm saying
specifically.
like, how do you
Yeah.
choose between like, say, this while loop versus recursion? Like, why would you, like why, if we know we can write this function and do the same thing two ways, why do we choose one over the other?
Oh, because the while loop is kind of like I want to say an option,
Yeah.
and the recursive filler is pointing out the maximum of what we're about to receive, or or that's completely off,
Now,
or what
I,
we're
yeah, I don't think so. Not quite there, because they're doing the exact same thing. There is no difference in like the result of this function and the result of that function. They're the same. It's kind of the how they do it. So that's sort of a hint as to like the decision we're making. All right, I hope it was good. Those are all good. Those are all good things. So when we broke the computer and it stopped working. Actually, I'm gonna do this so we don't do it again. But when we made the computer stop working, that's the kind of decision we need to make. We need to understand what sorts of things we have used here in our algorithm and what resources they use. How much resources are we going to need? How much available compute power, how much available memory, and all those sorts of things. That's a way to size it up. And the way this is done, this is also in the free resources, is something called Big O notation. So this concept we're going to spend a little time talking about. I'm going to show you this sheet. And this is something that is worth knowing because you will see it if you've done those algorithmic problem sets that I was showing you before. You may see people turn in their answers in terms of this. They'll say, here's my solution. And then they'll say size, time complexity, memory complexity, and then they'll use one of these O-N things. So this chart that I'm showing you here is big O notation. And big O, the O is from a German word, Ordnung, which means powers, orders of magnitude. But this right here is used by developers in developing interviews. So if you're looking to actually go deep into this world and become a developer and do it professionally, this is something you absolutely need to know. For anybody that's not looking to become a developer and is just looking to kind of understand this better, this is good to understand as a concept, and stick with this. Make sure that you do follow this, but there's no need to like calculate these things or know exactly how to, assign your algorithms big O notations. We're just going to go over the high level, what this is we're looking at, why you would need to look at this, why you would need to think about it. Right. So explain this chart real quick. This is talking about complexity, as it says up here, of the operations that you're running. So on the left-hand side here on this y-axis says operations going up, and that's the number of operations the computer has to do, right? So it's how much needs to be done by the computer. The x-axis is across the bottom left to right, the elements, that's how many inputs have gone into your algorithm, right? So as you can see, these lines up here that are labeled with these different things, there's this little O parentheses N exclamation points. That's factorial time is what that's called. And this is exponential polynomial time. These all have a name. Again, that's not the level we need to get to. I'm not trying to memorize these names. I encourage you to look it up so you know what people are talking about. That's really what this is about. But this is really saying that as the number of elements increase, the amount of operations increases by this black line. Right. So the colors here, if you can't see the little labels, the red is horrible, the orangish area is bad, yellow is fair, green, light green is good, and the dark green, this little tiny sliver, is excellent. So this right here is how people use, or how people compare one algorithm to another. They talk about the complexity in these terms. Is it making sense to everybody so far? All right. So again, as you get started, this is not something you typically need to worry about right away. As you're getting ready for coding interviews, if you're at that level where you say you knocked out those problems that we did, and you could do algorithmic problem solving in about 40-ish minutes at the most at the hard ones, then you should start thinking about considering if you did the best you could on these things, right? Because what they'll do is when you do a coding interview, they'll expect you to describe it in these terms. Say your CPU usage, your compute was whatever this was in time complexity and memory complexity. And they'll ask you if you could do better. So you got to know if you can do better, right? So that's one use for this. Another one, though, as we go through, as we go down and you look at this this chart below it, it says common data structure operations. So we're going to talk a little bit more about data structures. I promised that we would do that today. So far, again, we talked about data as binary. We talked about data as strings and lists and things like that. These are referring to slightly more complex structures most of the time. Some of the ones we've already talked about are on here, like array. Remember what this is? Anybody array in Python? What do we call them?
List.
List. Yes, very good. So whenever you see array in general computing terms in Python, that's a list. And then we also talked about this one, hash table. In Python, what do we call hash tables? Anybody? Give you a hint. Hash tables have key value pairs.
Dictionary.
Dictionaries. Very good. All right, cool. So we've talked about those two different structures, right? And those are on here. There's also a whole ton of these. I'm not going to go through all of these. Obviously, we don't nearly have time for that. But I do want to talk about stacks, queues, and arrays as an example, because these three are very similar to each other. They look very similar, but I want to use them as an example of what is being decided here. So first, I want to go over this chart a little bit, kind of explain what it's displaying. Right, it's got the same color coding as above, right? So the same green, yellow, orange, red. The very top, again, is data structure. So it's the name of the data structure here on the left. Time complexity is this whole first section here. And as you can see with the time complexity, it's broken down here between average and worst. And that's the average scenario, the worst case scenario. The idea being like, say, you know, the worst case scenario is if it has to go through every item in an array to find something if you're searching. Because down here on this row, it's different specific operations and how long those take. The idea here is that when you're trying to solve a particular problem, depending on what it is you're trying to do, you might look at this and say, okay, cool. Well, I want to have a list of things where I want to add things to this list to take stuff out of the list a lot really fast. And you'll see that compared to stacks and queues, arrays are not as fast at insertion, right? In both the average and the worst scenarios. So maybe you want to look at a stack or a queue. Everybody tracking? Is that making sense on what this chart is showing and what this is generally telling us? Yep. All right.
What's a stack and queue in Python?
Yes. So there, guys, great question. We're going to get to that. We're going to use some examples of not doing them directly in Python, but I'm going to try to draw them out a little bit and kind of show you what they are. So to do that, we go back to Bash console. I'm actually going to be in this Python console like we are here. So let me get, I'll get out of this and clear this up. So back in Bash, if you want to do this along with me, I'm going to enter a Python 3 console by just doing Python 3. So now I'm going to type in Python. I'm going to show you some things about lists and then talk about how a stack and a queue would be done in Python, right? So we're not going to implement stacks and queues. I'm going to warn you that now because it takes a little while to do it, and it's kind of an involved process. When you say, how does it look? And there's a little bit confusing on it. They can be done with lists, right? So you can actually just like we did with the main, or I'm sorry, with the recursive, the container filler and our recursive function, these things can be done with lists. But lists, again, according to Big O notation, will be very inefficient at doing these things. So I'm going to show you how lists do it, and I'm going to use that to explain what stacks and queues are, all right? So let's go through real quick and show some things that lists can do and how we would like add things to them and what that even really means, right? So let's start with a simple example list with just some data in it, nothing special. I'll just put a couple of letters in here, A, B, and C. And we'll close it off in square brackets. So we have our regular list. So all things, we talked about classes last time. All things in Python really are classes of some kind, right? So there is a list class out there, and we don't have to define it with this as we call literal, like literally like writing in a list. We could do another list and do the built-in list object that's in there, but we'll just do this with the list. So what that means to be a class, though, is they also have methods. If you remember, methods are like functions, but they're in a class. So lists have things that we could do to them that are built into it that allow us to chop them up. For example, like we can add things to them. We could take things away from them. So for example, if we want to take the thing off the back of the list, we can use what's called pop. and it'll remove the last element from our list. If we want to add something to our list, we can do append and put the thing that we want to append, so we can add our C back to it. We know that because there's now our list, right? So when I did these operations, so these are things, I want to show a couple of things here. The first is that these are built-in methods, and if you want to know the built-in method for like a string or a list, look in the Python documentation. It's got all these things written out. It's really, really useful stuff. But pop and append, those are pretty commonly used. The reason I bring those up, though, is because what's happening here, if you recall, when we set a variable on this row here, we set the variable, we did a named space in memory. So in our memory, we set aside a thing. We said, okay, this thing is going to be an array. And this array will not change sizes. So we say it's mutable, it changes. But if the stuff that we change makes the list smaller or larger, the computer picks that whole list up and moves it to another space in memory. And that operation of doing that and moving it over is slow. It costs something. So this right here would be a way, Corey, to answer your question, if we wanted to implement a list or a stack or a queue, which again, I'll show you what those are conceptually, this is how you could do it with a list. This is something that these operations exist. But Python is going to have something that's like built into it where you can use stacks and queues in other ways, right? So let's go to just our text here. And I'm going to use this as a way to sketch out what stacks and queues are so you understand them conceptually. Now we understand that lists can be chopped up and moved around, but they move in memory, and that is the expensive part. That's why they're slow to do these things. What stacks and queues are conceptually, though, let's talk about that just for a second. So first of all, let's talk about stacks. Or no, I'm sorry, let's talk about queues. Queues are much better place to start. So we think about a queue, and I'm doing this in comments in our main function because we're not going to implement a queue. It's going to take a little bit too long for us to write all the code that would make a queue separate from a list. But keep in mind, like I said here, you can't accomplish this with a list. It's technically just slow under the hood. So if you want to do something like a queue, you can use a list. Just keep in mind, if you have as many inputs as Google, it's going to be slow. If you have as many inputs as like Hired Labs, you'll probably be fine. All right. So queue. As a thing, imagine a movie theater, right? And it's got double doors. And outside of this movie theater, there is a line of people. And again, I'm going to use a list to remind us that lists can be used in Python to make a queue exist, right? So we could do that. So we could say there's 3 people in our line, and there's space for more people at the back of the line because they enter up here, right? As more people come up to our line, they're going to come in over here on this side. So they're going to enter the back of the line, and when the door opens, they're going to come in the front of the line, right? So this is called a queue, where things come in from one side and they stack up and they come out the other side, right? So this side is called NQ, and the other side is DQ. QUE. Aurelius, what's the question?
I said right to left and not left to right.
Man, that is an interesting question. I have no idea. I was thinking about humans moving from left to right, but it could be the other way. That was kind of arbitrary. The thing here to keep in mind is just that one side of it, this could have been the other side. That was an arbitrary choice. There's no reason it has to be this direction. But good question. The main takeaway, though, is that one side is where people enter, and then the other side is where they exit. Meaning that the first people to come in are the first people to go out, right? And so this is called sometimes first in, first out, FIFO setup. So a queue is this, right? So when we say that a queue is faster than an array, in computing terms, what we're saying is that we want to do this sort of thing. So if we're writing an application, if we're not thinking about a movie theater, let's say in an application sense, we want to write something that does customer service, and it matters when people show up and ask for service and what time they got there. So they're going to have a timestamp. This person's going to have the first timestamp. This person will have a second timestamp. And you, as a developer, have to decide how you're going to make this system of queuing these people so that the first person comes out and you do something with it, and the next person that comes in is added to the line. So you want to do a first in, first out construction. Now, again, you can use what's built in with lists, and you could pop things on the back, or you can append things to the back. So this could be the operation used to add people. If you want to add someone you want to have people leave the front, then you could slice them off the front or do something like that. But again, every time you do this, being the developers that you are, you know that this is picking up the entire list and moving it in memory. And so there's a faster way to have Python do it by using their built-in, they have a queue object, and it'll set up the data under the hood as a queue. And again, there's a whole somewhat more complicated way to implement it. The main takeaway for this class is to understand that you can get this done. You can get this sort of thing done. You could build a program that makes a customer service queue like this and does this, and you can accomplish it with a list, which you already know how to use. You already know exists. But be aware that at some point, if you have a huge number of inputs, it may not be the best solution, that you may want to explore looking into something in Python that's built in as a different type of data and not use the array at all. Does that make sense about what queues are versus arrays? Any questions about that?
So with the array, we would primarily utilize this before. Is there a structure at all of like if we utilize it before a queue or after? So or like does
Not really.
yeah.
Like if you use it, if you use it as not the thing that is being queued and dequeued, right? If you're not doing this operation on it, right? If you build an actual queue data structure, and that's again, it's a little more complex of telling the computer to keep a flexible amount of space. This little thing here is really what it's doing. And instead of storing it as an array, the computer will think of this thing as something that can, flexibly be different memory sizes, whereas an array is one size of memory. Does that answer your question, or does that just further confuse things? Good? All right.
Yeah, it's good.
Good. All right, cool. So the other one that I want to talk about again as something that can be done with an array, but is not particularly fast depending on the operation that you want to do, is the stack, right? So a stack, stacks, queues, and arrays. The reason I, again, talk about those three and hash tables specifically, which we mentioned in dictionaries, I think probably well enough, but we may talk a little bit more about them. The reason I talk about these is because they're very, very common ones. So as you're learning these things, if you're getting through, again, the problem set that we sent out and you're just about the next level of things, this really is that very, very next thing to learn, right? So if you've got a real solid handle on all the syntax that we did up to now, this is slightly the next step. But it's good for everybody else who hasn't totally grasped those things up to now to understand that there are ways to do it, and there is a formal way of understanding which one is the best way to do it, right? So there's different approaches. So, but again, let's make sure that we're asking why along the way. So it's more important that we understand why we're doing these things than we get through each and every example. So a stack. So let's think of this as we're going to start with, again, we're going to use a list again, but this is going to be a stack of plates, like in a restaurant, right? So imagine it's a big stack of plates, and these don't have a number because we don't really care. One plate's about the same as the next. And so this one, to kind of address it right away, I put the left side as where it's arbitrarily deep. So this can just kind of go on forever, right? So this is in a stack construction. So imagine a scenario where there's somebody washing dishes over here, right? And they're adding plates to this. And then there's somebody on this side, say, I don't know. Well, I should probably comment this out if I don't want to break my code, huh? Let's do that. Somebody down on this side, it's like a line cook that's taking plates off of it, right? So all the plates, sometimes this line cook takes 3-4 plates, depending on how many tables he's cooking for, whatever, how many people at the table are, whatever the case may be. So he may take multiple plates. Dishwasher may put a whole stack in there, but they're only coming in and out of this one side. That's it. So nothing ever goes down in and out on this side at all. And so this setup is called a last in, first out setup. And this is best accomplished with a stack data structure, right? For these reasons that we talked about, because given enough elements, it'll be faster to do these sorts of things in a stack than it will be with a list. But you can accomplish this like we talked about in our bash console, where we pop things off of the back and we appended them on the back. This right here, using just pop and append, you can make yourself this last in, first out construction. Just understand, again, it'll be slower. And why would we do this in a real world application scenario? This could be sort of like an undo function in an app. Like, so you're typing something and, you hit Control Z. This is the sort of thing that will remember the keystrokes that a user put in and give them the ability to like wind backwards through that. Whatever they just put in last is the first thing that's removed. So that's why you may want to implement a stack. That's what it's called, to set your data up to function this way. Keep in mind, if you have a lot of inputs, it may slow down. It may be better to not use an array to do it, but to use a stack instead. Any questions about that?
Yes. Why did you indent so far over when you went to the second line?
This one right here?
Yeah.
Oh, these are all comments. This doesn't matter. This is just
Oh,
a
okay.
visual thing. It's like, I just wanted to show that this is happening at the same end that things are added to.
Oh, so you're not actually creating any type of function or anything?
No, this stuff is
Oh,
all
okay.
commented out. These are just some visual representations of it. Because again, implementing an actual queue in Python would take probably more than our time together because it's a little bit complicated, and implementing a stack take a little bit longer than we needed to as well. And they don't look substantially different from a list. That's the other thing. When you actually write these things in code, stacks and queues, they don't look all that different.
Okay.
So going through the implementation is less important than understanding, again, what they are theoretically, so that you know what a queue versus a stack versus an array is. That knowledge is important, to just have that and know what they are and know why you would choose one versus another. Whoops. Stack. Aurelius, what do you got?
So the main difference between a queue and a stack is the order that it goes in and out of, correct? But the stack is the last that's on top of it. That's the first one that goes out. And the queue is the first that goes in it, is the first that goes out.
Yep, exactly. And that's why a lot of times, sometimes people think about stacks as like, pancakes or plates stacked vertically or something like that. Might be an easier visual to kind of keep track of. That you pick up the one that's right on the top each time and you stack them straight on that same top spot.
So when you're a full stack developer, like, what is it that you're doing?
Yeah. That's funny because that's got nothing to do with this stack. But the full stack is really what we're going to be doing. We'll be doing full stack development starting next week, where we do both back end and front end is what it's called. So we're going to disambiguate those terms if you haven't heard them before, but generally a little foreshadowing. Back end is anything that your users probably aren't going to be messing with, whereas front end is the place where users go and press buttons and click around and things like that. So front end is generally kind of your layouts, color schemes, where things are on the page, how big buttons are, whereas back end is more like what happens when you press the button, what the database is doing, that kind of thing. So full stack is somebody that does from the database end of it where users are not to the front end where the users are. And we're going to do exactly that, full stack, starting next week. So, but that oddly has nothing to do with this stack. So, good question though. Anything else? Any other questions about those things? All right, cool. So that's data structures. Again, we've talked about, to be very clear, data as ones and zeros, bits and bytes. That's what it always is, no matter what. Then there's data types as far as arrays and strings and all those sorts of things. But then we talk about structuring it in slightly more complex ways. Then we start talking about stacks, queues versus arrays, what that means. So data structures are somewhat higher level of that. We didn't even talk about trees or any of those, but it gets really cool depending on what you're trying to do. The other thing that I want to talk about, we said that this week is about algorithms and data structures. So we've talked about algorithms before. We're not going to go as in depth into this. So don't worry. It's not like we're starting a whole fresh new topic or anything. But I wanted to highlight that when people talk about algorithms, especially when you're getting going and you're trying to get a handle on these terms, it gets kind of confusing because they'll use it as we have just up to now about writing the processes to, make a peanut butter and jelly sandwich or solve the problems that we sent out in the coding challenges, algorithmic problem solving where we write your own. The other sense, and the sense that is on this chart, is named algorithms that are so common that people use them for specific purposes by name, right? So if you look at this list, it's just for sorting arrays. So all these algorithms, and this is definitely not the full list of all sorting algorithms, but this is just to get, like, so we have an array, we got a list in Python, right? let's say we get it all jumbled up and we want to sort it. This is just different ways to do that, right? And so the ones, it's really definitely worth a look at this and kind of learn some of these, like quick sort, merge sort, and bubble sort are probably like the 3 big ones that you might do. But what's really cool about this and this big O cheat sheet is that all these are hyperlinked to the Wikipedia page, which has all kinds of crazy explanations. But if you look over here on the right-hand side, and I'll click on this and see if I can make it a little bit bigger, it's got a cool little animation of the algorithm and what it's doing. So, you know, if you get like visual, you like more visual stuff, this is quick sort, and it kind of walks through what it says and what it's doing. And then of course you can read about this in probably more depth and detail than anybody would want to. But then here's all the things about its performance again. So we know this O to the n squared. We've talked about that already. This is the big O notation. So here it is over here on the right. And this is how these things are talked about, right? So this is useful to look at to learn and understand, to get these things. Another category of algorithm, again, this is sorting algorithms. Another one that's worth knowing, at least by name, and recognizing and understanding sort of how and why you would choose one over another, is search algorithms. So another thing, we're not going to implement any big search algorithms or learn how to do it, but there are kind of 3 big types of search algorithms that are worth knowing what they are kind of by name a little bit, so you recognize them and understand what they are in comparison to each other. And so the first is linear search. And that's meaning like starting at the beginning, going all the way through, right? That's really, really slow. So that's if you have, imagine an array or a list and you want to find something in it, its worst case scenario is if you have like 1 million things and the thing that you're looking for in your search is not in that array at all. It has to go through each one of the 1 million things before it knows for sure that it's not in there, right? So linear search is slow. Best case scenario is the first thing on the list, and then it's really fast. That's great, but nobody cares about the best case scenario. It's really slow. So that's the thing to really know about that. The other one that's very commonly talked about, and it's good to know, is binary search. And this is much faster, but it's by no means like the fastest way to do it. Like I could probably not misspell search, huh? So binary search. And this, if you think about an old school dictionary, like a paper dictionary, I don't know if anybody's even used one of those in the last decade or two, but the way that those work is binary search, right? So think about that. If you're looking for a word that starts with a letter in the first half of the alphabet, you're not going to waste your time even opening the second half. You're going to open somewhere maybe in the middle and then look forward because you know it's in that first half, right? And then maybe you open up again and cut it in half and look again in the half that you know that it is, right? Maybe overshoot a little bit. That's what binary search does. So it takes your data set, imagine again, it's an array, and it cuts it in half, and it uses the built-in, we've done it before. I think we've used it before with in. If not, it's demonstrated. We still have this list. This works with any collection like the list, the dictionary sets. But if we do like, we have A, we know is in our A thing, so it comes back as true. We know that F is not, but we just use the word in. And this is built into Python, so reserved words, built into most programming languages, and generally it just like checks for presence of that thing. So what binary search does is it leverages that common ability with computers to split your array in half, your data set in half, and then see which half it's in. If it's in the first half, it does that again, splits in half. So this is much faster than linear search because each time it goes through, each iteration, as it recursively, usually these recursive functions, goes through, it cuts the data set in half. So it's much faster. That make sense? And then the last one that's worth knowing, we've kind of mentioned it already, is hashing, which is the fastest way to search. And that is using dictionaries, hash tables, things that we've talked about before, relying on key value pairs, right? So the ability to look something up quickly by its key. Think of that as the way that we look things up now by definition. If you look up the definition of a word, if you're anything like me, you just go to Google and look for the definition of the word, right? That's what Google's doing. It's much quicker at indexing that way, looking up just specifically that key, getting you the value, than having to cut any data sets in half or reiteratively go through and recursively do a function that's, again, slow. Recursion is slow. So you may not want to do things recursively. You want to do it with hashing. Something that's very, very, very worth knowing in this world of hashing things is something called JSON, JSON. So this is JavaScript object notation. I mentioned it before as being the key value pair set up just like dictionaries, but it's from JavaScript. But this is used absolutely everywhere, right? And it's based on this hashing thing. So these are kind of the main things to know about search and search algorithms, linear search being slow and why it's slow, and the choices that are being made when you choose any of these sorts of approaches to solving your problems. Any questions about any of that or any of the things we've covered up to now?
So when would you use JSON, or that's just something to know as far as like the scripting and stuff is concerned? Or-
Yeah, so it's when you want to change data, like move data from one place to another, like out of your database or connecting two systems together, it's an exceptionally common way to send data around all over the place. Because again, it's like, let's say, for example, you have a new piece of software and you need to update that software with whatever information is the old software. You could pull it out and put it in JSON format and manipulate it that way. And it's just widely used. So it's something that's good to be aware of, knowing what it is, that it exists, and you'll probably end up running into it if you do any sort of programming of any kind, really. And that's your question. And there's
Yeah.
cool. There's some cool tricks we can do with it later once we have our database up and running. We can talk about it more a couple of times, but it's just one of those things that it is a hash table. It's really common, and the reason that it's so commonly used is because hashing is fast. So it's a good way to store huge amounts of data pretty quickly. So, and well, for quick access.
One more question.
Sure.
Sorry.
No.
So
Yes.
so when developers or engineers are fixing their code and they're Googling and stuff, so basically they're hashing. Is that correct or no?
I mean, that's a very vast oversimplification of how Google does its search. But I use that as an example to compare looking in a dictionary for the meaning of a word versus looking for the meaning of the word in Google. That
Oh, okay.
that if you go like just grab just that one word and pull it back is what Google is kind of doing, as opposed to like flipping through a huge thing and cutting the data set in half like you would do in a paper dictionary. Does that make sense? Cool. Yeah, I was gonna say the thing that Google's doing is more based on like a natural language processing thing where it does the weight of the number of times the search term you put in appears in a document, and it's term frequency, inverse document frequency, but that's a different thing altogether. Cool. Any other questions about these things? Because this is the majority of what we want to cover for today. I did want to show, kind of demo what we're going to be building next week, and make sure again that we got plenty of time to answer questions. Make sure that everybody can get to most of these things mechanically. They can get into your Python anywhere. You can get into your Bash consoles, because we're going to be building next week again in our Bash console. We're going to start running some more commands in here and building the app straight from here. Any questions?
Can you resend the day 3 recording? Because I want
Yeah,
to go back over building a list.
sure. Yeah, absolutely. So also, and if you that's a good thing. If you're not on Discord yet, I'll resend the thing there, and all the recordings are posted in the resources channel in Discord as well. So I'll send that out as a reminder, and I can resend. I'll just reping you from last week, the day 3 with that recording, so you have it. And then, oh, there's something I was gonna say that just came up, but I forgot. Must not have been important. All right. Anything else? Any other questions? Cool. All right. So feel free to shout them as we go. I'm just going to show real quick and start talking about kind of what we're going to be doing next week. Show us where we are. Again, we will start building from here, from the console. So make sure you can get to your console, get to you're comfortable using these things. And if you haven't been doing the stuff up to now in Python anywhere, if you've been doing it like on your own computer in the command line, which is fine, that's totally cool. This is going to, like, what we do next week is going to be deploying to the internet. So the very first day, like on Tuesday, we're gonna have an app on live on the internet that you can mess around with and look at. It's not gonna do much, but it'll be there. And that's only really gonna work if you build it right here in Python anywhere, right? So I encourage you to start doing it here if you've been doing it on your own computer. But just to show you what we're gonna be doing, I'm gonna go over to my web tab. So next week when we come in, we've gone through dashboard, consoles, files. Now we're gonna go over to web. We're gonna start our web application, and don't worry, I'll go through all the setup of this. I set this up earlier today just as a quick example. Again, it's not a design class, so it's not going to look pretty. This is more about the function, but We'll show you how to grab some stuff off the internet, slap it in your website so we can do different types of media. We have a couple of pages to talk about how to navigate between things. But the bulk of the application itself is going to be a to-do list application where we're just going to have tasks. So right here, we're looking at the read function. We don't have any tasks, but we'll be able to add things. Say new task. We can add a due date. Give ourselves plenty of time. So now we see that we have a delete button. We can see its status. We can update it. Say that we wanted to set that to complete. So we got our read, we got our create, we got our update. Then we hit delete. We'll get this little JavaScript warning that says, hey, are you sure you want to do that? And we'll say, yeah, we do. And so the JavaScript that's in there is really just kind of show you how to plug it in and put the place in there. We could do all of this without JavaScript, but I want to make sure that we touch it, handle it, know how to plug it in because it is really, really useful on the internet. But that, in general terms, is what we're going to start building. This is the end state of it. It's going to take us a bit to get there, but we're going to start building the framework or the groundwork for this next week. Any questions at all about what we covered, where we're going, what we got up to now? All right. Cool.
I have a question.
Not too late now. No, I'm joking. What's the question?
For the list we did build, we supposed to go to files to go back to look at them. And then when I click on the list, it sends me to a page that says directories and files.
Uh-oh. Yep. So it should be, if you're writing along with this, then we go to directories and files. It would be just in your main directory. You should just scroll down until you find the main.py, if that's where you're writing them. That's where you're
Right.
Yep.
Okay. Let's try it again.
But, and also if you want to hang out a bit, I can, you can share your screen. I can see if I can help you directly as well. Anybody else that might be stuck, same thing for you as well. Any other questions? General or specific?
I'm there. It was just the file I used was weird. Okay. Thank you.
Okay, cool. All right. Great. Well, then nothing else. We can wrap for tonight, a few minutes early, and leave you. There's, again, all you got plenty of stuff to work on. So get through those problem sets, practice these things, and reach out with questions, and we'll start building our app next week.
Cool. Thank you.
Yep. Thank you.
Thank you.
Thank
Take care,
you.
everyone.
Thank
Have a good
you.
one.
Yep.
Bye.
Have a good weekend, y'all.